So today we have Dr. Pandit from Indian Institute of Science, and then there will be more talks in 2026. We have one scheduled for February. Dr. Sidney Redner will be speaking. I wanted to remind everyone that the deadline for submitting the t-shirt design is December 20th. This is for early career scientists, graduate students, and postdocs. We have the image of the month, which is a research publication highlighted monthly. Please make sure that you are aware of this. And we have early career spotlights at DSNP. We are always looking for volunteers, so if you would like to get involved with DSNP, and especially for the upcoming March meeting, please make sure that you sign up. We will put the link to the sign up in the chat. I would like to remind everyone that during Zoom, due to security concerns, attendees are not able to unmute themselves and ask questions, but if you have any clarifying questions, please put in a chat box, and one of the hosts will interrupt the speaker to ask the question from them. Other major questions should be saved for the end of the talk. After the talk, you may raise your hand or put your question in Q&A, and one of the hosts will unmute you so you can ask the question from the speaker. So I'm going to stop sharing and pass it to Menon.
As Shima said, it's a great pleasure today to host Professor Rahul Pandit, who's a theoretical condensed matter physicist. He is currently the National Science Chair at the Indian Institute of Science in Bangalore, where he has spent much of his career. Rahul was recently appointed APS Fellow through DSNP, and the citation reads, "For important contributions to challenging and fundamental problems in statistical and nonlinear physics, and for extensive service to the community." So in his service to the community, amongst from much institutional service to his own institution, he's chaired the Committee on Statistical Physics of the IUPAP, and he served as Vice President of the IUPAP. Another piece of service is that he has successfully mentored many generations of PhD students who have gone on to have valuable, important contributions to the community in faculty positions all over the nation. The important contributions to challenging and fundamental problems, including understanding of the statistical physics of turbulence of various kinds, to mathematical models of instabilities underlying, for example, cardiac dynamics, and more generally to spatiotemporal chaos in extended dynamical systems. Aside from studying the science of these systems, he's also contributed deeply to developing numerical techniques to attack these very difficult problems. Today we're going to hear about another set of problems. He's going to tell us, which we're going to hear from him very soon. As Shima said, please jump in and put your questions in the Q&A. We'll be happy to relay them. Rahul, the stage is yours. It's a pleasure to have you here. If you would like to share your...
Sure. Thank you very much for inviting me to give this talk. It's a pleasure to share some of our work with you. So I will just take the application window, I guess. Oops. Can you see my screen now?
Yes, we can.
Hello?
It's not. Yes, we can. It's not in presentation mode, but we can see the screen.
At least let me make it full screen. That's somewhat in between. All right. So shall I start?
Yes, please.
Hello. Okay, so I'll be talking about the Cahn-Hilliard-Navier-Stokes framework for multi-phase fluid flows of laminar, turbulent, and active. And all this work would have been impossible without very active collaborations with lots of people: John Gibbon, Nadia, who's now in Germany, Kiran, who is in Nice, my student Biswajit, who's here, Vasant is in Switzerland, Prasad is in TIFR Hyderabad, Noirita in IIT Kharagpur, Anupam in IIT Hyderabad, and Dario Vincenzi in Nice. We've published several papers on various aspects of this problem, but I will not, of course, give you all the details. But if you would like a bird's eye view of the sorts of problems that I will be talking about today, you can look at this article which just came out in JFM on this very subject.
Rahul, to interrupt. Yeah.
So, yes.
I'm afraid your
Hello?
slides are not advancing.
Oh,
We only see your title slide.
that's peculiar. So there's a huge lag. Either that or, okay, I don't know what to do.
This is slide 2 now,
Probably
the collaborators.
Yes, slide 2, but that means there's a huge delay. Okay, now you see collaborators, now you see publications, which is not important. But do you see this slide now with JFM perspectives?
Not just yet.
It's still on collaborators.
Wait. Let me try something. Let me see which network I'm on. Oh, 1 second. Excuse me. Just give me a few minutes. This should... Oh.
Yeah, the voice is coming through with no lag. But the slides are not updating with...
I wonder if we disable the video, maybe it gets faster.
With which one? The cell phone?
The video. So let's try once without video.
Without... I mean, I turn off my video.
I should say that
sure.
Zoom has turned your bars from red to yellow while we've been talking.
Is that right?
Something positive is happening.
I'll turn off the video.
It's turned, your bars seem fine actually now.
Yeah.
Okay.
If you could try sharing again.
Shall I unshare and share again?
Yes, right now you're not sharing. Yes, so please share again.
Oh, all right.
Sorry, folks. It's best that we sort this out right in the beginning so that...
Probably we should have tried even earlier. Shall I just share the entire screen, or you think only application window is best?
Application window is best.
All right.
Sharing the entire screen is heavier.
All right, sure.
Yes, references now.
References, okay. Does it change slide now?
Immediately.
Okay, good. So something happened. All right. So
shall we risk putting you back on video again, or?
No, don't.
Okay.
That's all right.
So in the upper left, there's a switch that says fit width. Maybe we could fit height.
No. Let me just do full screen. Is
Even
that better?
Even better.
Even better. Thank you.
Okay, good, fine. All right. So here's a quick outline of my talk, an introduction, then generalized Cahn-Hilliard-Navier-Stokes equations, some illustrative results, then some mathematics if we ever have the time, and then conclusions. So I hardly need to tell all of you that there are lots of examples in the physical world of multi-phase flows. Here is the one that everybody would like to solve. Inside a cloud, you have moisture droplets and water vapor and so on. But I don't think we can get to those scales yet with the methods that I'll be using. Then let me show you some other things. You've all seen droplets of oil and water, which are on the left, and another very interesting object called an antibubble, which comprises a shell of a low-density fluid inside a high-density fluid. This goes back to the 1930s, but I will show you a simulation of it based on Cahn-Hilliard-Navier-Stokes. Are the slides changing properly now?
Yes, perfect.
Okay, so then there are ternary fluid examples also. There are compound droplets, which are often used for modeling white blood cells in blood, and bubbles passing through interfaces. I might not get to all of those today. And you also get very interesting effects when you confine active fluids, to which I shall get to eventually. Let me see if I try a movie and it works. Does that movie work?
Yes.
Okay, that's a droplet of Bacillus subtilis forming a spiral vortex, and there's a similar one where this droplet with E. coli, the center of mass, does a random walk. So now let's get to the main topic. If you read texts in fluid dynamics, you will get, the word multi-phase flows means different things to different communities. So here's a very influential and good overview article in the Annual Reviews of Fluid Mechanics. It says dispersed multi-phase flows are distinguished from other kinds of multi-phase flows, such as free surface flows. In dispersed multi-phase flows, the evolution of the interface between the phases is considered of secondary importance. Processes such as droplet or bubble breakup and agglomeration do indeed alter the interface between the phases. However, in the context of dispersed multi-phase flows, one accounts for the interfaces between these in terms of a particle size spectra, without considering the detailed evolution of the interface. So we will do just the opposite in this talk. We will restrict ourselves to systems in which different phases coexist in thermodynamic equilibrium, and where it is necessary to account for the surface tension and the breakup or coalescence of droplets of these phases. And to understand such multi-phase flows, we must combine theoretical methods from both fluid dynamics and statistical mechanics. So I'm not sure how much of this slide you can see, but don't worry about the details. The simplest way to understand phase coexistence is, for example, to go back to the Ising model, which is in this box here, with upspins and downspins. And then you do Curie-Weiss theory, which leads you to a free energy which depends on an order parameter m sub I. I'm allowing it to be inhomogeneous. Then you carry out a gradient expansion, and you get a Landau-Ginzburg free energy. If you are now interested in conserved order parameter dynamics, that leads to the Cahn-Hilliard equation, which all of you must know, I guess. The sorts of problems I will talk about have phases in which you don't merely have a binary mixture, but the two components of the mixture are fluids. And therefore, if you want to understand the complete fluid dynamics, you have to couple the Cahn-Hilliard equation with the Navier-Stokes equation, and that yields the Cahn-Hilliard-Navier-Stokes equation, which I will talk about today. But before I go there, let me remind you of some statistical mechanics, which perhaps you would cover in a graduate level statistical physics course. Suppose you have a homogeneous binary mixture which undergoes spinodal decomposition and forms two distinct phases, A-rich and B-rich, that are supported by a diffuse interface. So the Cahn-Hilliard system, you don't even need Navier-Stokes to begin with here, captures the dynamics of these interfaces, and the system phase separates, as you can see in this movie of phase separation. A rich is red and B rich is blue. All right? And this is the elementary theory of such an interface. All of you must have seen Landau-Ginzburg functional, where the surface tension effect is captured by this grad phi whole squared term. So that gives you the cost for interfaces. And this V phi is a double well potential, for example, phi squared minus 1 whole squared, which has two minima. One corresponds to A rich, the other to B rich. And phi changes continuously as you go from A to B. So this is a typical homework problem. For example, if you want to do the mean field theory of a simple interface, let us say that the interface is such that you have one bulk phase at minus infinity, another bulk phase at plus infinity. Then you ask for the interface, which follows by taking a functional derivative of the free energy functional that I introduced in the previous slide, and then saying that you have variation only along the y direction. That leads to a second order differential equation, which with these boundary conditions you can solve, and you get a tangent hyperbolic interface. But now we have to confront the fact that we have a binary fluid. So let's recall, I mean, if it were just a fluid, you would have Navier-Stokes. So here's the velocity. So that's the Navier-Stokes equation, du dt, u dot grad u. Here's the pressure term. Here's the viscosity. If you have gravity and friction, you can put those in. But here's the important term where the order parameter phi is acting back on the fluid. The fluid is incompressible. And the order parameter phi that distinguishes between A rich and B rich phases is governed by this equation. You would have good old conserved time-dependent Ginzburg-Landau here, were it not for this u dot grad phi term. This u dot grad phi term gives you how the order parameter phi is advected by the fluid. All right? There are various parameters here, which I'm not going through in detail, but we can look at them. And the important ones are psi, which sets the width of the interface, and the surface tension, which really gives you the cost of forming an interface. Now, if you talk to engineers with this sort of a framework, they will say, well, experimental measurements show that the interfacial thickness is a few nanometers. And so this diffuse interface that we will get from the Cahn-Hilliard-Navier-Stokes framework is not very good. But there are various mathematicians who have shown that you can take the limit very carefully, and it might require very big simulations if you eventually simulate this, so that the interface width is sufficiently small that you can make meaningful statements about various experiments. The good thing about having a diffuse interface is that you do not have to match, do boundary conditions on an interface that moves in time and which has a complicated spatial dependence also. But the price you pay is that you have many more dimensionless numbers. Were it only a single fluid, you would have a Reynolds number, but now you'll have to worry about Peclet, Bond, Ohnesorge, capillary, Cahn, Weber. We won't do all of them today. There's Reynolds, of course. The Cahn number is a dimensionless measure of the thickness of the interface. The Weber number is inversely proportional to the surface tension, and so is the Bond number. Okay? Bond number occurs in examples where we have to worry about gravity. And L naught and U naught are characteristic length and velocity scales. All right, we can do several direct numerical simulations. I won't bore you with the details. They are standard pseudospectral simulations, but they take a lot of cleverness, and it helps to have graphics processing units and very good graduate students who can program in CUDA. So now let me just give you illustrative results that you can get from this Cahn-Hilliard framework. So first, let's look at binary fluid turbulence. All right, we will look at multifractal droplet dynamics first. And if you look at a droplet in such a flow, all right, so I have shown you two illustrative droplets in these insets. This is a more or less circular droplet. This is all in 2D, where the surface tension is sufficiently high that in spite of the flow, the droplet is more or less circular. But when the surface tension is very low, the droplet gets pulled out. And if it is very, very low, it will even break up into multiple droplets. Now, if you try to quantify the deformation of this droplet, then you can do so by finding its perimeter at time t, normalizing by the perimeter of an undeformed droplet, etc. And if you plot this deformation parameter gamma versus time, you see that especially at low surface tension, you get this very, very intermittent signal. And not surprisingly, if you do a full multifractal analysis, you find that indeed it is multifractal. And this, as far as I know, had never been done before we carried out this analysis. So the turbulent really makes the droplet deformations multifractal in a way that we can quantify using this framework. The other thing that turbulence does, and I will illustrate it here for two-dimensional turbulence, is to arrest the phase separation. You will remember that I began with a video in which the two phases separated and you got something which was A ridge here black and B ridge here white. Now what turbulence does is, you see, normally if you want the two phases to mix, in a conventional binary fluid, you have to go above the critical temperature into the one-phase regime. But here, let us say you start in the two-phase regime, but you churn up the flow by turbulence, which you can now do because your Cahn-Hilliard equation is coupled to the Navier-Stokes equation, and you see that turbulence remixes the two fluids. You can characterize this remixing by calculating various lengths. The simplest is to compute the density-density correlation function, which I have denoted by S of k here. So if you look over here, I have a sum over all k. K is a wave number, so this is circularly averaged, divided by ksk, so this is obviously a length, and we call this a arrest length scale. So basically what turbulence does is it doesn't let the sizes of the phase separating droplets become infinitely large as they would in the absence of turbulence, but it makes it finite. And there is an old prediction due to Hintze in the context of droplet breaking, and that says that the sizes of the droplets should scale as the surface tension to the 3/5. And indeed, this LC, once you decipher all the technicalities in this plot, we find that LC does scale as sigma to the 3/5. So this Cahn-Hilliard-Navier-Stokes framework is helping us to understand coarsening arrest, and we can even pick out the Hintze scale. Now, those of you who know turbulence, you will know that in turbulence, we often plot the energy spectrum versus K, and the signature of turbulence is that the energy is spread out over many decades. And here I show you how it varies in this particular case with the surface tension. But let me not dwell too much upon this. If there are more questions, I can come back and you can find a full quantification of this coarsening arrest in this paper, which we wrote nearly 10 years ago. Now let me show you this very interesting thing called an anti-bubble, which I showed you earlier, which was a low density sort of ribbon in 2D inside a high density fluid. So physically, what you think would happen is that, well, if you look at this little bubble, eventually the south pole will thin and it will break and so on. And you can keep track of what happens to the vorticity also. So here in the top panel, you have the density, and here's the vorticity. I will come back to the lower panel in a minute, but let me show you a movie, and I hope it will work. Can you see the movie? So you see the thinning at the bottom, and then the anti-bubble breaks. So as far as I know, this is the first time there is a full simulation of an anti-bubble. And indeed, you can even quantify many things in this anti-bubble. I will show you one quantification later. We can also do this in 3 dimensions. This is an experimental anti-bubble, a picture given to me by Chirag Karlelkar. And there also you see the same thing, a thinning of the south pole, a bump forming of the north pole. This is a section through a 3D thing. And you can, for example, investigate the dependence of the anti-bubble lifetime as a function of the surface tension. So this bond number is the reciprocal of the surface tension. And this lower panel, which I promised to tell you about, is to show you that if you do this simulation using the volume of fluid method, which engineers favor, which requires complicated boundary conditions on a moving interface, you get results which are similar. Now, let me show you another phenomenon. Let me just keep track of the time. How am I doing for time? I've gone through about
20, you have maybe 20 minutes to go or so.
20 minutes to go. Okay, fine. I will try not to go at the speed of light. Okay. All right. So, I will show you a phenomenon which is a sort of low Reynolds number turbulence, but induced by interfacial fluctuations, which we also get from this Cahn-Hilliard-Navier-Stokes framework. Let me remind you that a similar effect occurs when you add polymers to a fluid, and at low Reynolds numbers, you get something called elastic turbulence, which is induced by the polymers. There, the other control parameter that comes into play is the Weissenberg number. Here we will find that if we start with an initial condition in which you have these 2 components, light brown and dark brown, in a rectangular array, a crystalline array, and if you look at the vorticity, you have a crystal of positive and negative vortices. Then what I'm telling you is that if you make the surface tension sufficiently low, then even though the Reynolds number measured in the usual way is low, then the interfacial fluctuations will melt this crystalline array in the same way that turbulence is known to melt this crystalline array. I'm sorry, I'm using sort of condensed matter language, which fluid dynamicists often don't, connect with, but I think a lot of you are condensed matter people, so you will understand what I mean. So again, let me show you. So this is the initial condition, and you will see that after some time, the interfacial fluctuations will make the ordered array that we began with completely disordered, and you will get low Reynolds number turbulence in a binary fluid mixture just because we've made the interfacial tension very low. And again, it's not only beautiful pictures and movies, you can actually characterize this very well. I mean, you can look at time series here of the energy dissipation, and it is obviously disordered in time. You can do Fourier transforms, etc. And you can characterize it very, very well by using all the tools that we have developed for the study of the statistical properties of turbulence. So this is a completely new form of turbulence which had not been anticipated earlier. Now, let me turn to something which, has been enjoying quite sort of fashionable active matter. So now let me turn to a problem in which we have activity-induced turbulence, and I will show you that just like conventional turbulence, this will also lead to the arrest of turbulence. So how do we proceed? So there is, of course, those of you who know critical phenomena will remember that in the old days, we didn't call it Cahn-Hilliard-Navier-Stokes, we just called it Model H. It was in the celebrated Hohenberg and Halperin review in Reviews of Modern Physics. Over the years, the group of Mike Cates developed an active Model H, which I will show you how the activity comes in. And their model was different insofar as they were really interested in low Reynolds numbers and they had external noise. We will not have external noise, but we will just churn the fluid enough so that the turbulence will generate the noise dynamically. Okay, so this in the active fluid literature is called motility-induced phase separation, MIPS. And they did hydrodynamic interactions, but they are always in the Stokes flow limit. So back to our Ginzburg-Landau functional. Again, the quadratic term here, and here is the surface tension cost. You can see my cursor, right? Hello?
Yes, we can.
Okay, good. And psi is +1 is high density, psi -1 is high density. Now, how do we make this active? Now, here was the equation for the scalar, follows from the functional derivative of the free energy functional. Here is Navier-Stokes, but written in terms of the vorticity, which is just curl of U. And I put in a stress term here, which I've written out here. Don't try to do the algebra right away. It's not important. All I want to note is that if this coefficient zeta were exactly sigma, which is the surface tension coefficient in this free energy functional, then it would be just good old Cahn-Hilliard-Navier-Stokes. But we will now make this thing different from sigma, and probably it should be a multiplicative factor the way I've written it now. And what Cates and his collaborators argued in this paper, Tiribocchi and co-authors, this they used for a system, this would be positive for a system with extensile swimmers, and this would be negative for contractile swimmers. And we will consider the contractile swimmer case to study turbulence. And the first thing I want you to see is that as we increase this activity parameter, I'm now just showing you the modulus of it. So this is at low activity. Already you can see that the turbulence has been, the phase separation has been arrested. This is white and black phases, if you like. And as you increase the activity, this activity-induced turbulence is strong enough that it has mixed it up even more. and the lower panels show you the plots of the vorticity that go with these images. And again, it's not only words, you can quantify it. You will remember that I defined a coarsening length scale. Unfortunately, I've changed the notations here. This we get from a density-density correlation function as a function of the wave number summed over wave number. And because it's got an extra k downstairs, this is the length. All right, and here's the definition of the density-density correlation function. If there were no activity, zeta were 0, this length would grow in a way that is good old Lifshitz-Liousov theory as t to the 1/3, where t is time. But here it is arrested by this sort of active turbulence, and it asymptotes to some finite number. Okay? And as the mean length goes down with increasing activity, the Reynolds number defined in the conventional way based on this length scale goes up. Okay? So this is, if you like, active scalar turbulence, which again had not really been studied. You see, most of the active fluid or active matter people are typically working at low Reynolds numbers, and then they have external noise. But we have just taken the equations and, let them do what they do at high Reynolds numbers. And then you can ask, the fluid turbulence people are always looking at the energy spectrum. And a conventional fluid turbulence in 2D is sort of complicated. It has an inverse cascade and a forward cascade. And in the inverse cascade regime, you have a -5/3 law. Well, here also there is some sort of a -5/3 because this is a compensated spectrum, k to the 5/3 ek versus k on a log-log scale. The phi k spectrum also shows a power law regime. So we can characterize it again with all the methods of turbulence, and then we were brave and said perhaps our results are of potential relevance to a system of contractile swimmers, for example, C. Reinhardti. But here the story is more complicated because we are working with an experimental group, and the picture is not as simple as this model would suggest. If that statement sounds mystical, I can elaborate on it later. Now, what you can do with 2 components, you can try to do with 3 if you know enough about 3-phase fluids. The free energy functional becomes more complicated. You need 3 concentrations, C1, C2, C3, but since they are conserved, their sum should be 1, so that's one constraint. And you have to keep track of 3 interfacial tensions between phases 1 and 2, phases 1 and 3, phases 2 and 3. And again, there's an interfacial thickness. So a conventional statistical mechanician would probably draw a Gibbs triangle, and the vertices of this triangle are the pure phase regions. Again, please don't look at the details. All I want you to do note is that with a little bit of work, we can modify Navier-Stokes to have this 3-phase thing work out. And so once all the dust settles, what can you do with it? So let me give you an example of something that this formalism can do, which is to look at the evolution of liquid lenses. So let me tell you about liquid lenses. Liquid lenses look like this. There are 3 phases, a green phase, an orange phase, and a blue phase. And when the lenses come together, there is a height of the neck h, and this increases with time as t to the power 1 in the viscous regime and t to the 2/3 in the inertial regime. Now, so far, there was no real simulation of this. There is actually, that's incorrect. There is a lattice Boltzmann simulation, but I show you here results from our direct numerical simulations, both in 2 dimensions and in 3 dimensions. And you can see how you get a vortex quadrupole here, and it evolves in time. And that's nice for the pictures, but we can actually make it quantitative. And if I plot here a scaled height of the neck versus time, then it does cross over from t to the 1 in the viscous regime to t to the 2/3 in the inertial regime, where there is some bit of turbulence which does set in. Okay. Now, in the interest of giving you an overview, let me not look at all the details, but tell you that we have actually characterized this turbulence also in the usual way. But let me show you some other things that Cahn-Hilliard-Navier-Stokes can do. So it can lead to a self-propelled droplet. You remember this, I showed you the active Cahn-Hilliard model, where which leads to motility-induced phase separation, which I mentioned. Now we take 2 such scalars, a phi, which is a binary emulsion droplet, which would distinguish, let us say, from oil in water. And then there is a psi, which is an active microswimmer field. So here is the free energy. These are the usual terms. And there is an additional term, minus beta phi psi, which likes phi to be where psi is. Okay. Now, when you work it all out, okay, this is what the equations look like. Don't try to figure them out, but just have faith in me. We have done the correct thing. So you will see some very interesting effects. There is one activity parameter, which is the ratio of the coefficients of these stress terms. All right, sigma 2 tilde over sigma 2. Now, if there is no activity, phase separation proceeds by the formation of ring-like patterns, which you see at the top. And this is the top row. This was known to various people in the old days. There were some experiments in confined geometries, and the theoretical analysis was carried out by Hohenberg. But now we have activity. And at intermediate activity, you see that it forms some sort of a droplet, and then this droplet becomes self-propelled. And that happens because you get a sort of oscillating dipole, a vortex dipole, and this is how it propels. If you increase the activity too much, it sort of starts, fluctuating randomly. And it sort of propagates, but not as efficiently as it does as intermediate activity. So let me show you this movie. This is the self-propelled droplet, and you will see that soon it will start moving in some diagonal direction. You can see it's moving. And this is coming out of these equations. This boundary here, the magenta boundary, is the thing which distinguishes the phi, the oil from the water, and here is the active psi. And you get this beautifully translating droplet, which have been seen in some biological systems, but this is the first time I've seen it in this relatively simple model. You can characterize the propagation of these droplets in many ways, which we have done. And there is a crossover from, from ballistic behavior. This will move eventually ballistically to diffusive behavior if I make the activity too high. And again, the interfaces will show multifractal fluctuations, just as we found for droplets in conventional turbulent flows. All right. How much time do I have, Narayanan?
Maybe can we do 8 minutes more? Is that seem okay? We started a
Sure.
couple of minutes late, but I don't want
No,
to
no,
lose
no,
your
no.
audience at
No,
the
no, no.
end for questions.
Sure. That's fine. So let me not do interfaces that transport barriers. Let me show you a little bit about active spinner fluids. So there have been people who've been looking at such types of systems. I talked of C. Reinhardti. You can engineer uniflagellar mutants of these, and they spin only one way. Or you have two-dimensional crystals have been found in rotating cells and suspensions of the bacterium. Okay, this bacterium, I don't even dare to pronounce it. And people also have, Quincke rotors, which they can make. One rotor goes clockwise, the other one goes anti-clockwise. So can we write down a Cahn-Hilliard-Navier-Stokes equation for it? And the answer is yes. It was written down by these people in 2015. Excuse me. They actually did particle models, but they also noted that in some limit they could have a hydrodynamical model. So again, you've been seeing these models. This is the advection of a scalar by the velocity. Here is Navier-Stokes, but I won't go into the details. There's an additional term, tau del squared phi. Tau is like a magnitude of the torque. This is in 2 dimensions. So both the tau and omega, they just point either out of the plane or into the plane. So our recent work on this, one has just been published and another is at least available in the archive. We can simulate. So let me just show you something that this does. This is a schematic. So we have 2 phases, one in which the predominant direction of rotation is clockwise and the other is anti-clockwise. And suddenly in the fluid, you start seeing these doublets, vortex doublets, okay? And as you increase tau, you see that initially there is phase separation, but as you increase tau, you induce, if you like, a rotor-induced turbulence. And, well, it's turbulence. And what is most remarkable is that at large values of tau, the vorticity becomes proportional to phi. Okay, so this was a finding. I mean, the earlier authors had just not pushed this calculation into the high turbulence regime. They were looking at the low phase separation end of things, but we found this very nice form of turbulence where omega is proportional to phi, for which we also developed a theory, which I will not tax you with just now. And we managed to, characterize the turbulence in many, many different ways. Let me just show you one, which is reminiscent of what we just saw, that the coarsening arrest length scale decreases with tau and the Reynolds number increases with tau. So tau is inducing a new type of turbulence, which is rotor-induced turbulence. But it also does something very interesting. If the mean value of phi is different from 0. So if phi is equal to 0, we get turbulence, the mean value. But if the mean value is, let's say, 0.5, then at large values of tau, we first form these vortex triplets. You see, this is a vortex triplet. If you scan through it, you will see this profile for the vorticity. And these vortex triplets spin, and they form a good triangular lattice. And if you're a condensed matter physicist, you'll take a Fourier transform and find the reciprocal lattice of a triangular lattice. Okay, so there's an emergent active crystal of vortex triplets. All right. But it's not orientationally ordered, as you will see in this movie. So first nothing happens, and then you see these vortex triplets forming, and they spin around and spin around and spin around. And if I just speed it up a bit, they form this vortex crystal where each one of the entities is spinning around, but they're not in phase. The way it is set up, the mean vorticity has to cancel, so they all cancel. And so I think of this as a non-equilibrium plastic crystal. Some of you might remember that, some mesogenic crystals systems first show positional order and only later orientational order. The classic example is methane. So it first forms a crystal, but the methane molecules keep on spinning around because of thermal fluctuations. But here we have, fluctuations from this turbulence. So they organize into what would be conventionally called a plastic crystal. Now, before I end, I just want to show you that there is room in this trade not only for physicists and engineers, but also for mathematicians. We have a true blue mathematician here. And you can ask for the regularity of the solutions of the 3D Cahn-Hilliard-Navier-Stokes solutions. You know that this is a celebrated problem for the Navier-Stokes. If you can solve it for 3D Navier-Stokes, you'll get $1 million from the clay math people. So the analog of this, you can ask, and without going through all the details, let me just tell you that if you look at the Euler equation, there is a celebrated equation called the Beal-Carter-Maida theorem, which gives you the condition under which you do not have a singularity. That is, if the maximum value of the vorticity integrated over time does not diverge until t star, then it is regular. But if there is a t star at which it becomes infinity, then it is not regular. So we were able to derive that sort of an theorem for the Cahn-Hilliard-Navier-Stokes case, where instead of the vorticity, we had the maximum or L infinity norm of the energy. Here is the surface tension part, the double well part, and here's the kinetic energy. And we could check that various conditions hold in numerical simulations also. Last but not least, we have also used neural networks to predict flow fields from concentration fields, which we do by training our neural networks on configurations from our simulations in the Cahn-Hilliard-Navier-Stokes system. And we've even tried it on experimental data, so that it's not very easy to measure flow fields in multi-phase flows. So here it's much easier to measure concentration fields. So we have a scheme by which our trained neural network can, just given the concentration fields, can give you the flow fields. So with that, let me end, and I thank you for your attention, and I show you a little movie to keep you amused. I'll be happy to answer questions.
Thank you, Rahul, for an excellent talk. Folks, if you want to ask questions, you can either put them in the Q&A, or if you raise your hand on Zoom, we can unmute you and have you ask questions. Rahul, while people are getting used to this, may I ask something?
Sure.
You
Please,
warned us
course.
early on that well, actually, let me go to someone who's raised a hand.
Okay.
Can we have Alexander Wagner? May I just, would you please ask your question?
Okay, let's see. Can you hear me?
Yes, I can hear you.
Yes, excellent. It's a very nice talk that you gave. And at the very beginning, you were talking about the connection between the more microscopic models like the Ising model and the Cahn-Hilliard models that we have.
Yes.
And I'm fascinated by, but don't fully understand the transition that you do, and particularly, so you say there is a way of doing an expansion to obtain these free energy models, but at the same time,
Yes.
there's this disagreement between the interface widths, and then you get this slightly more extended interfaces that don't seem to quite match what you have in the microscopic level. So I was wondering what's known about that.
Well, I mean, the mapping that I talked about is standard, and if you want to see it worked out in pedagogical detail, you can see this article I referred to in JFM Perspectives that we just wrote. Now, the interface width in the full Cahn-Hilliard-Navier-Stokes framework depends on many parameters. So the dimensionless measure is the characteristic scale and the interface width. So if you really wanted to get into the regime that engineers would like, eventually you would have to do very, very large simulations so that you can resolve a thin enough interface. At a practical level, you don't want your interface to be sharper than 3 or 4 grid spacings on whatever grid you have with your collocation points. We do pseudospectral, so that's at some level the best you can do. But still, if you really pushed me and said, I want a really, really thin interface, I would have to do a really, really big calculation. But, you know, you can get many things right, at least qualitatively, without going that far, as I showed by all the examples that I went through. Did I answer your question?
Yes, there's one more sort of follow-up with respect to that, because the microscopic models, of course, will have fluctuations, right? Whereas the fluctuations
Well, yes.
are in some sense averaged out in these Cahn-Hilliard models,
So,
right?
not with Navier-Stokes, you see, because most of the ones that I've been looking at here, there is turbulence. And the turbulent fluctuations overpower the thermal fluctuations more or less like they do in conventional turbulence. There are a few papers now, Greg Aing, Nigel Goldenfeld, etc., which say that we have to worry about the thermal fluctuations deep in the dissipation regime, but we are far away from all this. I mean, the turbulence is so strong, thermal fluctuations don't really matter. You also saw that in the active Cahn-Hilliard-Navier-Stokes thing where I told you, Mike Cates, etc., and his group, they did the low Reynolds case. That's really Stokes flow. There they need the fluctuations. But we are at very high Reynolds numbers or effective Reynolds numbers. So thermal fluctuations are not really important as far as I can tell.
Yeah. Thanks very much, and thanks again for the great talk.
Thank you.
There's another question. I think you're unmuted if you want to go ahead.
Can you hear me?
Yes.
I can, yes.
Thank you. Wonderful talk. Learned.
Thank you.
It's a very, very rich field. Let me concentrate on the example that you gave about the self-propelled active bubble.
Okay, sure.
Where does conservation of momentum enter?
Oh, it's there in Navier-Stokes, but actually, I didn't tell you every detail. In that particular case, we did have some friction.
No, but presumably there's a conversion of
well, I mean, here are the equations.
Which then essentially acts as a force propelling the droplet forward.
Yeah, that's in these stresses, which I have written down here. So it is these stresses which are pushing it. In this particular case, because it is in a two-dimensional case, in all the two-dimensional cases, there is bottom friction. So there is friction. So strictly speaking, there is no momentum conservation. But it is these active, what shall I say? These active terms which lead to, so the psi is the active field. I mean, unfortunately, there is confusion of terminology. The active matter people use activity in this way, whereas fluid dynamicists call an active scalar a scalar which affects the velocity field. Now, this particular scalar psi is active in both senses, active matter and fluid dynamics. Phi is active only in the fluid dynamics sense, not in the active matter sense.
So,
And
so
it is
presumably,
yes,
the time dependence of the spatial variation of psi is what then gets converted into
yes, absolutely,
into the forward motion of the. Okay, thank you.
Absolutely. I didn't go through all the details, but if you look at this picture, if you ask for what is the flow field doing when this droplet starts moving, initially there is a quadrupole, and the quadrupole doesn't lead to motion. But then it turns out that the quadrupole annihilates and you get an oscillating dipole. And the oscillating dipole propels this thing, if you want to work out the details of the fluid interacting with the concentration fields. Okay?
Okay, thank you.
Thank you.
May I suggest we're at a minute or two past the hour? So maybe this,
Okay.
if Rahul doesn't mind staying on to answer questions, that's great, but maybe we can call it if that's okay. But maybe we can
That's
thank
fine.
him again before the audience has to leave for an excellent talk.
Thank you very much.
Thanks very much, Rahul. But do you mind hanging on 5 more minutes in case people
No, I can hang on. There's no problem.
are around? And I know it's very late night for you.
That's 11. Yeah, okay.
So please, if there are other questions, actually, I have a more naive version of the first question that was asked about diffuse interfaces. Are they? This is where you gain so much by this technique, right? By not having a sharp interface, is there by not imposing a boundary condition? Is there a place in all these things where you pay the price for this, or microscopics never enters in any of these examples?
No, you pay the price because, I mean, what I'm saying is if you're a careful person, then you will say, do it for many different values of the parameters. How does it change? You change viscosity, what you get. You change surface tension, what you get, etc. So then to do a systematic study, you have to do all those cases. And in some cases, it makes a big difference, which is also a physical relevance. I mean, here I'm showing you, if my screen is still being shared, the height of the neck of those coalescing lenses. And they cross over from t to the 1 to t to the 2/3. Okay? But that happens only if you change viscosity. If you didn't change viscosity, you wouldn't see this. Okay?
But presumably there'd be a control parameter dependence to this phenomenon, even if to the Ohnesorge number, even if you were doing this with a boundary, right?
Yes, of course, because Ohnesorge, let me remind myself and you what Ohnesorge is. It is nu square root of rho divided by sigma L naught. L naught is a characteristic scale. So
and
yes,
it's not
even
something
if
in
you
which
were doing
sigma, sorry.
Yeah, so psi did not enter. So
Right.
here the interface width did not enter. So yes, if you did it by some other means, let's say volume of fluid or something, it would come. But you see, in volume of fluid, you can never really break an interface. So you would have to patch the lenses together by hand. Just like when we did the antibubble, we had to break the antibubble by hand in the volume of fluid. Whereas here, the physics of wonderful Cahn-Hilliard-Navier-Stokes makes the South Pole thin on its own, as it must. Okay, so for some things it's good. Okay.
Yeah, this one was particularly remarkable to me because you are tracking an interface that's a lens with a sharp slope.
Yeah, yes, sure. But it, it does give what is experimentally measured. I mean, those experimental plots for the height are look very much similar to what I've shown you. Like this one. And we had other parameters which they don't even measure, which we can measure because we are doing simulations. But this crossover thing is a characteristic of lenses. We've also done droplets, which are circular, where the power laws are different. And that also comes out of these things. As do many, many other things which are still unpublished. You get lots of nice oscillations after droplet mergers and so on. But someday we'll write it up.
Please,
Okay.
there was another question. Please go ahead.
Sure.
Oh, at several points in your talk, you refer to turbulence. I noticed that you have used DNS for some of the simulations. To what extent are your results dependent upon turbulence models? K omega,
No
K epsilon?
No modeling. It is pure direct numerical simulations.
It's all DNS. Okay.
It's all DNS with
Okay.
the pseudospectral. So it's the best quality DNS short of resolution, which is all that we can afford in Bangalore. But, you know, it's good enough for the phenomena I cover. I'm not doing the world's record-breaking high Reynolds number simulations.
Let me ask then a variation of the question.
Sure.
Suppose I want to be a poor man's turbulence guy and I can't afford DNS. To what extent do you think your results will survive going to simpler turbulence models?
Okay, then I guess, for example, let me take, some of these things you could try some closure. So I don't know whether the rest of the audience might not know closure, but I'm sure you do, like EDQNM, right? So suppose you did some EDQNM type closure in the turbulent state, you would get some set of integral equations for the energy spectrum and the density spectra and so on. And then if you put them on a computer, again, those integral equations, if you want to get quantitative data, you would get, and then the spectra would come out, and some of it would agree, some of it would not. I mean, EDQNM is good for fluid turbulence if you are just saying, oh, I want a Kolmogorov type power law, but if you want multi-scaling, that will not come out of EDQNM, etc.
Right.
The usual things.
There's a question that was written out in the Q&A. Sorry, I didn't mean to interrupt you.
No, please go ahead. I mean, I'm fine.
May I read that out? It says, very interesting talk you mentioned about experiments on chlamydomonas, which are pullers. In one of the Cates papers, they describe contractile swimmers that orient perpendicular to the gradient of the phase speed variable, which breaks the interface and generates new interfaces. Are you referring to this behavior when you mention experiments with the chlamydomonas?
Not really, because they were looking at very low Reynolds numbers. Of course, their Reynolds number is based on the size of the, I guess it's an algal suspension, C. Reinhardti's algal. But we have pushed it much further into turbulence land. They had an external noise, so they were looking at motility-induced phase separation. But again, we have a paper on the archive. I didn't put the reference here, done with Prerana Sharma's group in our department. The first author is Prince, who's a graduate student, where we have looked at experimentally, we've just done the analysis part of algal turbulence, which occurs in these C. Reinhardti systems, except they have both types of swimmers, extensile and contractile, by looking at mutants. And there, our simple theory doesn't cover both cases. But yeah, that's the sort of turbulence. I'm sorry, I should have put that reference up here, but the first author is Prince. It's on the archive, 2025, and it's got algal turbulence in the title.
Thank you.
Was that too big? No, okay.
Yes. Is there a follow-up to this? Is that that's
no.
good? Okay. Maybe we're now at 10 past the hour, and we've kept you
Mhm.
till almost midnight. So maybe this is a good time to
Okay.
thank you
All
again
right.
and
Well, thank
to
you for
end this
having me
webinar.
here.
This is
And
uh,
I
uh,
liked very much all the questions that I got. Thank you very much.
thank you. So just for the audience, I've put the link probably in a few days, this lecture will be posted in case you wish to share it with other people or revisit it. Sorry to both the audience and to Rahul for the few minutes of teething problems, but I think everything went
That's
well
all
after
right.
that.
Okay, fine. Thank you very much.
Bye. Thanks again.
Okay. So I stop sharing now.
That's great. Thank you.
Okay, fine. Thanks a lot, Narayanan. Bye.
Of course. Take care. Bye, everybody.
Yeah,
I'm
bye.
good end at this
See you.
point.
Yeah. Okay. Bye.